Hey folks, the Earthlings. Welcome to Decoding the Earth, the podcast where we dig deep into the layers of our planet to uncover the fascinating stories beneath our feet and sometimes even above our heads. I'm your host Raihan Ghani, a geologist and professor here to bring the rocks to life. Each episode will explore how geology shapes us by shaping the world around us. Ready to decode the earth? Let's rock. Big news today, October 8, 2025. The Nobel Prize in Chemistry was awarded to three scientists for the development of metal organic frameworks, or MOFs. The Nobel Committee praised their molecular architecture with rooms for chemistry, materials whose vast, tailor made pores can trap, sort, and transform molecules with surgical precision. Why this prize and why now? In short, MOFs have matured from an elegant idea into a platform technology touching water, climate, energy, and environmental cleanup. Think of MOFs as crystalline scaffolds. Metal ions form the corners, organic molecules are the struts, and the result is a porous crystal whose cavities you can program for a job: capture CO2, harvest water from the desert air, destroy pollutants, or store gases. What exactly are MOFs? They are not powders in the everyday sense, but precisely ordered frameworks, metal nodes linked by carbon based ligands to create vast internal surface area, like a hotel with millions of identical rooms per grain. Swap the metal or the linker, and you change the guest list. The molecules that fit, bind, or react inside. Geology meets MOFs. Yes, really. Here's the part I love as a geoscientist. Nature built MOFs before chemists did. Two rare minerals, stephanovite and zimzus-nikovite, turn out to be the natural MOFs. Their frameworks are built from iron and aluminum centers bridged by oxalate ligands, with the pores occupied by hydrated sodium and magnesium cations. These minerals occur in unusual carbon-rich permafrost and coal environments in Siberia, biogeochemical settings where oxalate can be generated and stabilized. The discovery that MOFs can be found in nature in these rare minerals has been considered a paradigm shifting event in the field. It gave us a geological lens on MOF stability, water interactions, and even proton conductions. From rocks to remedies, MOFs for climate and water. Example 1: water harvesting from desert air. Some MOFs take up water at very low humidity and release it with mild solar heating. A standout is MOF 303. Field demonstration in California, including Death Valley, have produced hundreds of grams of water per kilogram of MOF per day using only sunlight. The secret is how water molecules assemble inside the pores at specific humidities, filling and emptying with fast kinetics. Example 2: carbon capture. A different MOF family, amine appended magnesium frameworks, capture CO2 through a cooperative mechanism. Above a threshold pressure, CO2 inserts into metal amine bonds and triggers chain formation, giving that beautiful step uptake ideal for scrubbing flue gas. Environmental remediation, like clean water and cleaner air, MOFs also show promise in PFAS removal, those persistent forever chemicals. Zirconium MOFs, such as MOF 808, have demonstrated strong adsorption of PFAS like PFOS and PFOA in water thanks to tunable pore chemistry and robust framework. Reviews from past year highlight how functional group inside these pores can be engineered for selectivity and regeneration to make or break features for real remediation. And yes, gas storage remains a classic MOF strength. High surface area materials like MOF5 set important benchmarks for hydrogen and methane adsorption, useful for smoothing renewable energy with hydrogen or packing more natural gas at lower pressures. What ties all this to geoscience isn't just those natural MOF minerals. It's the broader idea that porous frameworks, from zeolites and carbonates to oxalate MOFs, are part of Earth's toolkit for moving and transforming molecules. In the subsurface, porosity governs fluid flow, reaction fronts, and storage. MOFs give us a designed analog of those geological framework. Crystals where we can tune pore size, chemistry, and flexibility to targeted jobs in water and carbon cycle. The Nobel today recognizes that MOFs have become a universal language for porosity, bridging mineralogy, material science, and climate technology. So, what next? From a geoscience vantage, three things matter. One, stability in real environments. Salts, fluctuating humidity, and fouling are the field geology MOFs must navigate. Two, scaling and life cycle. We need green synthesis and clear end of life plans so we are not trading one environmental problem for another. 3. Integration with earth systems. Pair MOF water harvesters with local hydrogeology and solar flux. Pair MOF carbon capture with geological storage or utilization pathways. The point is to couple the pore scale magic to planet scale impact. Today's Nobel tells a story. Design the right rooms and you can host the right chemistry. Whether that's catching CO2, pulling water from thin air, or filtering stubborn pollutants. Nature has been doing this in minerals for a long, long time. Now we are learning the language and writing new chapters. I am Raihan Gani. This is Decoding the Earth. Keep your curiosity alive, your questions coming, and your eyes on the pores. They are where the action is. Wishing you a happy Earth. A special thanks to Professor and Geologist Nahid Gani for directing and producing this podcast. Don't forget to subscribe and follow us on social media to stay up to date on all things geology. See you next time on Decoding the Earth.